Let me tell you a little bit about polynomial functions and their graphs. Let me start with some examples of polynomials. F of x equals 3x squared plus 2x minus 5. That's a polynomial. F of x equals 2x to the fifth minus 1. That's a polynomial. Lines, those are polynomials. 3x minus 2. That's familiar to you guys. You know that the graph of that is a line. Turns out that a line is a polynomial. So are constant functions. Okay, so these four, they're all examples of polynomials. Let me give you a more general definition. So a polynomial is a function that can be expressed in the following form. Okay, so each of these coefficients here, each of these a sub something, okay, a sub I, these guys are all real numbers. And each of the exponents is either 0 or a positive whole number. Okay, so I should say 0, or I should say a non-negative integer. Okay, the highest power that appears in your polynomial is called the degree of the polynomial. And another term we have associated with polynomials is called the leading coefficient. The leading coefficient is the coefficient of the highest order term. Okay, let's take a look at the examples I gave you a little bit ago and identify each of these properties. Okay, so for this polynomial right here, 2 is the highest power that appears, so the degree of this guy is 2. The leading coefficient is the coefficient of the highest powered term. This is the highest powered term, and so the leading coefficient is 3. For this guy right here, the degree is 5. The leading coefficient is 2. For this polynomial right here, the degree is 1, and the leading coefficient is 3. For the constant polynomials, the degree is 0. Okay, so 3 by itself, well, we can really think of it as 3 times x to the 0 power, because x to the 0 power is 1. So the degree of a constant polynomial is 0, and the leading coefficient is that constant, which is 3. Okay, let's take a look at the graphs of some polynomials. Okay, so let's take a look at the graph of f of x equals 3x squared plus 1. Okay, I'll just draw a rough graph. I won't be too precise as far as, so we know that this is a quadratic, so we know that its graph is a parabola. I won't be completely precise about how wide it opens. So it's going to look something like this. So here is the y-intercept of 1. Okay, so there's a rough sketch of the graph of that polynomial. Okay, another example is f of x equals negative x to the fourth plus 2x cubed. Okay, this is a degree 4 polynomial, and the leading coefficient is -1. And the graph of this looks like this. So you see that polynomials of degree 2 or more give us nice examples of nonlinear functions. Okay, next I'm going to talk about a couple of concepts associated with functions. The first of those is the notion of increasing, decreasing behavior. Okay, a function is increasing on intervals where the y values are growing as you move from left to right. Similarly, a function is decreasing if the y values get smaller as you move from left to right. Okay, so this function here, as we trace along the graph on this portion, we see that the y values are falling. Okay, so this function is decreasing on the interval from -infinity to 0 because it stops decreasing once we get along the y-axis, and that's x equal to 0. And then the function grows from then on. So this function is increasing as we start at 0 all the way to infinity. Okay, so you see when you list the intervals or the places where a function is increasing or decreasing, those are the x values that correspond to the portion of the graph where it's growing or where it's falling. Okay, this function here, as we go from -infinity, it's growing, 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 growing until we get to this x value. And then from this x value all the way to infinity, the function is falling. So it's decreasing from this x value all the way to infinity. The next concept that I'm going to talk about is the notion of extrema. Okay, there are two types of extrema. The first of them is the notion of local or relative. These two are used interchangeably. Local extrema or relative extrema. And the other is global extrema. So within the class of local extrema, we have the notion of a local minimum, we have the notion of a local maximum. For global, we have a global minimum and a global maximum. Let's start with the local minimum. A local minimum is a point on the graph where all neighboring y values are higher. Okay, so this guy right here, if you look at all the neighboring y values, you see that this y value here is the smallest. So this y value, we'll say, happens at 0.2, is a local minimum of this function. You're going to notice that this graph, or this function, also has another local minimum, a point, a y value, where all neighboring y values are higher. And that's this y value here, which happens at -1. A local maximum is a y value where all neighboring y values are lower. Okay, so it's kind of, if you will, a little peak of the graph. This happens at 1, so 1, the y value of 1, is a local maximum of this graph. Okay, so in this case we have 2 local minima and 1 local maximum. We can have multiple or we can have none. Okay? Let's move to global extrema. Okay, the global minimum is the overall lowest y value that the function has. So if we look down this graph, keep going, going down, we see that -1 is the lowest y value that this function takes on. So -1 is the global minimum of this function. The global maximum is the overall highest y value that it takes. This goes on forever in this direction and forever in this direction, so there is no highest y value, which means there is no global maximum.